Hello, welcome back to the lecture series in wave optics. In last lecture we have discussed the basic concept of diffraction phenomena. Basically that is the bending of light at the sharp edge of an obstacle. Then we recall the concept of Huygens theory, Fresnel assumptions. We also discussed how the rectilinear propagation of wavefront using Huygens-Fresnel assumptions in last lecture. Today we will discuss how the diffraction from an edge of an obstacle. Suppose this is an obstacle. Now a wavefront is incidenting on this obstacle. Suppose the light is incident on the edge and we expect a shadow this region, but when we view the shadow through a microscope, the edge of the shadow shall not be a sharp one. It look like this. You can see the bright region, then you can see above that there will be a dark region, then bright region. You observe a alternate dark and bright region in this picture. That means it really means there is a bending of light phenomena take place and a pattern formed, and obviously this pattern is the diffraction pattern. So in this session we will discuss how the diffraction effect due to a straight edge. Now we will take the same figure as an example. Suppose S is the source of monochromatic light which is passing through a narrow slit, and a sharp edge of an opaque obstacle like a blade is placed in front of the path of light as shown in the figure, and here we assume the screen. This one is the screen, and this screen we are assuming the screen is perpendicular to the plane of this board. So you can visualize this screen which is perpendicular to the screen. Now a sharp edge is placed in the path of light in such a way that the line joining the slit to the screen at point P meet at this edge. Here this line is meeting. In the absence of diffraction, the light due to the sharp edge, there should be a uniform illumination above the point P. This point should be a uniform illumination of light if we are not considering the diffraction, and below the point P we are expecting a complete darkness, right. We know that there will be a diffraction effect at the edge, therefore the diffraction pattern formed on the screen. Let us see what is the principle of that diffraction pattern. In order to discuss the theory of this type of diffraction, let us take the distance A to P as B here. Now with reference to the point P, the wavefront can be divided into large number of half period zones. Here half period zone A M1 is the first half period zone, M1 M2 is the second half period zone, and M2 M3 is the third half period zone, and so on. Now we have already been discussed the construction of half period zones in the last lecture, and you know that in between two alternate half period zone there will be a path difference of lambda by 2, and by the concept of the Fresnel-Huygens assumptions. Now you can say A is a point that can be taken as a pole of the wavefront with reference to the point P. Now A M1 and M1 M2 M2 M3 etc. as the first, second and third half period strips or zones here. So with increasing the order of the strip, the area of the strip decreases. The theory behind this we have already been discussed. Now you can take AP is as point the distance as B, then obviously the distance PM1 that shall be B plus lambda by 2, because between two alternate zones there will be a path difference of lambda by 2. Then obviously PM3, the distance from here to here, and PM2 shall be B plus 2 lambda by 2, and so on. Now let us check were the maxima and minima formed in this diffraction pattern? For that, let us take another arbitrary point P dash on the screen. So, I took this P dash as the point on the screen. Now, let it be P dash the point on the illuminated portion on the screen, that means above the point P, that is the illuminated portion, below P we are expecting the geometric shadow. We have to calculate the resultant effect at point P dash due to the wavefront xy. So, xy we are expecting a cylindrical wavefront. So, in order to calculate the resultant effect at point P dash, let us join the line S to P dash. So, this S to P dash is meeting at point B on the wavefront. Therefore, B is the pole of the wavefront with reference to the point P dash on the screen. Now, the intensity at point P dash is our point of discussion. There are few points to be remembered here. So, first, this intensity at point P dash depends on the number of half period strip enclosed between the points A and B. So, this is the first point to be remembered, and the second thing from the Fresnel-Huygens conception, the point P dash will be maximum intensity if the number of half period strips are enclosed between B and A is odd, and the intensity at point P dash will be minimum if the number of half period strips enclosed between B and A are even it is. Now, moving to the calculation, here the distance between the slit and straight edge we are taking it as A, and B is the distance between the straight edge and screen. Now, we have to calculate what is the path difference here. Now, the path difference between two superposing beams, so one wavefront from point B and another from A, so wavefronts are meeting at point P dash, what is the path difference between the wavefront from B and A? So, that we have to be calculate. So, that path difference is simply, it is path difference delta is equal to A P dash minus B P dash. We are expecting we know that A P dash is the longer path, and you can have the simple geometric trigonometric calculation to calculate have the value of A P dash and B P dash. So, here you are just considering the triangle A P dash P, and from there you can have the A P dash as root of B square plus X square and minus, now the B P dash is the distance from here to here. So, therefore, you are taking it is the S P dash, that is the distance from S to P dash, and minus S B. So, this is the value of B P dash. Now, you can again calculate root of B square plus X square minus what is the value of S P dash can be taken from this particular triangle. So, this is a right angle triangle. So, from this right angle triangle you can calculate you can have the value of S P dash, that is a square root of A square plus B square plus X square, this will be plus X square and minus A. If I am taking this, I am rearranging this formula like this, I am writing it as B square plus X square all raised to 1 by 2 and minus, and from here I can write it as root of A plus B, root of A plus B all square can be written as plus X square all raised to 1 by 2 minus A. Now, from this I can take B square as a common factor under root from this raised to 1 by 2 term from this bracket, and here I can take yeah, this is common bracket over here. Yeah, we are taking this B as a common factor from the bracket. So, this will be B into 1 plus X square by 2B, X square by B square all raised to 1 by 2 minus, now this from here I am taking A plus B as a common factor, then A plus B into 1 plus X square by a plus b all square all raised to 1 by 2 and minus a. Yeah, now this formula can be rearranged, or that can be written as like delta is equal to, the path difference delta is equal to b into 1 plus x square by 2, that raised to 1 by 2 term I have reduced like this to b square. Now then minus, then we have the second term a plus b into 1 plus x square divided by a plus b all square, yeah, 2 into a plus b all square. So here also we have written like this, and all minus 1. So this is the term we have, and we have the bracket over here. Yeah, we have a cross bracket over here. So this will be b into 1 plus b into 1 b plus, now that will be bx square divided by 2b minus, now we have a plus b into minus, that will be minus b here it is minus into a plus b will be minus a plus b into x square divided by 2a plus b all square, and here it is minus into minus, that will be plus a. So here this b and minus b will be getting cancelled out, this a and this a will be getting cancelled out, and we have the formula like this right now. Well, this was b square. So this b and b getting cancelled out, a plus b and a plus b square is getting cancelled out. So I can take is x as a common factor. So this will be x square as a common factor here. So that will be 1 by 2b minus 1 by 2 into a plus b, and yeah, 2 also can be taken as common factor if you need, dividing by 2. So now it is so simple to take the LCM of this from here, and you can easily have the delta value as the path difference delta is equal to x square by 2 into a divided by b into a plus b, yeah, b into a plus b. Well, so this is the equation for the path difference we have here. Yeah, this is the path difference x square by 2 into a divided by b into a plus b. The point p dash will be of maximum intensity if the path difference delta is equal to half odd integral number of wavelength lambda. Now we can substitute the value of the path difference ax square divided by 2b into a plus b. Here I am using this xn over here because here you know the value of n varies as 0, 1, 2, 3, 4 etc. So we will be giving the positions, we will be giving more number of positions, therefore I am taking it as xn. Xn means it is the position of the nth maximum intensity. So that is equal to 2n minus 1 lambda by 2. So from this formula you can have this xn square as 2n minus 1, then taking this term as on the right side, then we will be getting lambda b into a plus b divided by a, where xn can be written as square root of 2n minus 1 lambda b into a plus b divided by a. This here lambda for a monochromatic light lambda is a constant value, b and a we are in the experimental setup, that is also a constant value. So I am taking this entire term as k, under root k, therefore under root term I am taking it as k, therefore xn is equal to k into 2n minus 1. That means the position of the nth bright band at point P is directly proportional to under root 2n minus 1. Similarly, we can have the point P dash will be minimum intensity when this path difference is equal to 2n into lambda by 2. Again I am substituting the value of this path difference over here, a xn square divided by 2b into a plus b, that is equal to 2n into lambda by 2, that, or simply you can write it as n lambda itself here. Now you can we can have the position of the nth minimum intensity can be square of the nth minimum is 2n into lambda b into a plus b divided by this a. So if I am taking the square root, I will have the position of the nth minimum intensity, that is xn, that is equal to under root 2n into lambda b into a plus b divided by a. So in the same way here lambda is a constant factor here for a monochromatic wave, b, a and all are constant, I am taking it as k. Therefore xn is equal to k into root n. That means the position of the nth minimum intensity is directly proportional to square root of 2n. We have this equation for maxima like xn is equal to k into root of 2n minus 1. So in case of a diffraction from a straight edge, so here S is the source, this was the straight edge and this was the screen, and you know the diffraction pattern will be looking like this. You can have a bright band on the screen initially, then alternate dark and bright regions will be forming, and in the region below P, that there we expect a geometric shadow. Here we are not getting a sharp shadow in this region. Here the intensity of the light gradually decreases. Let us see how the position of this maxima and minima. For example, you know that xn is the position of the xn is supposed to be the position of nth dark maximum intensity region or nth maxima. So that is equal to k into root of 2n minus 1. We have discussed it. Here k is the constant. If I take n is equal to 1, then we will have x1 is equal to k. So this will be 2n minus 1 will be 1, right. If I take xn is equal to 2, then this x2 is equal to 4 minus 1, that is 3, root 3, and x3 can be root 5k, etc. This is the position of the third maxima. This is 5. And so on. Now how the separation between the successive maximas are there. So if I take x2 minus x1, this is the distance between two second maxima and first maxima, that will be root 3 minus 1 k. So that will be 0.73 k. If I am taking x3 minus x2, let us see what is the width over here. So that will be, if I am taking root 5 minus root 3 k, that will be 0.50, yeah, here it is k there, 50 Kelvin, 50 k. You can see that the width between the second and first was 0.73, then third and second one is 0.5, and it gradually decreases if we take further x4 minus x3 and x5 minus x4, that gradually decreases. That means we see that with increasing the order of the the separation between the consecutive maxima decreases. That means the fringes comes closer as it is shown in the figure here. So a similar effect can be seen in the minima also. Now we will discuss how the intensity varies, especially the intensity at a point inside the geometric shadow. In above the point P in the illumination region, we know that we have the alternate dark and bright zones or maximas or minima. So now we will discuss how the intensity at a point inside the geometric shadow. For that we are taking a point P dash over here. Now P dash is a point below P, that is in the geometric shadow. Now with reference to point P dash, B is the new pole. Then half period strip below B are supposed to cut off by the obstacle. Only the uncovered half period strip above the point P in this particular region, the half period strip or half period zone above the point B will be effective in producing the illumination at a point P dash. Now as P dash move further from point P, then more number of half period strip above B is cut off and the intensity gradually falls. Thus within the geometric shadow, the intensity gradually falls off depending upon the position of P dash with respect to P. The intensity on the screen due to a straight edge can be seen like this. So above the point P, this is the illuminated region. In this region the intensity varies like this. So here the effect will be increases, and on moving away from point P, then the effect due to the wavefront decreases gradually, and in the point below point P in the geometric shadow, the intensity gradually decreases and becomes dark, and then finally it's fall off gradually in the region of geometric shadow. And according to the wave theory, the shadow caused by an obstacle in the path of light are not sharp, and what it does mean that the rectilinear propagation of the light is only approximate true. In general, there is a gradual fading of the intensity in the region of the geometric shadow, and with monochromatic bright and dark bands, that is the diffraction bands, are observed in the illuminated portion on the screen. However, with the white light colored band, the colored bands will be observed, and the bands of the shorter wavelengths are near to the point P. So this is how the diffraction pattern form when we use a white light. How the diffraction pattern due to a narrow slit. Here you see there is a slit AB here, there is a point source, that may be another slit. You are getting either cylindrical or a spherical wavefront that is incidenting on the slit, and that is spreading through this slit, and we are expecting a illumination region in between E and F, and above E and below F, this region and this region we are expecting the geometric shadow. Now how the diffraction pattern formed, that we will be discussing considering two cases. One, if the slit AB is wide, considering a cylindrical wavefront incidenting on the slit, and this can be divided into large number of half period zone by using the Huygens Fresnel assumptions, and how the resultant intensity at point P will be. So this is the wavefront over here, and this can be divided into large number of half period zone, and what is the intensity at point P depends on the based on the discussions we had in the last lecture, that the amplitude at point P will be equal to m1 divided by 2. This is the resultant amplitude at point P. So, M1, what is M1? M1 is the amplitude due to the first half period strip from this region. Thus, the point P will be illuminated. Even the points very near to P will be equally illuminated. If the wavefront is divided with reference to the points near to the point P, the number of half period strips above and below the new poles in the exposed portion of the wavefront will be quite large. Hence the result in hence we are getting an illumination, a uniform illumination in this particular region. A uniform illumination we will be getting. Now let us consider a point P dash. Now this P dash I am taking on the screen here. Now P dash is near to the edge of the geometric shadow, and we are assuming the slit is wide. Now let us join the point S to P dash. Now that is meeting at point here, over here. Now this is the pole over here. Now that is the O dash. Let me take this point as O dash. Now O dash is the pole with reference to P dash. If the wavefront is divided into half period strips, the number of half period strips between O dash and B, this region, between this region, the number of half period strip between O dash and B will be quite large, and the illumination at point P due to the lower portion, that lower portion of the wavefront will be same at all points near to the edge of the geometric shadow. But the intensity at point P due to the exposed portion of the wavefront between O dash and A will depends on the number of half period strip between present, if it depends on the number of half period zones is odd or even. If the number of half period zone is odd, then the P dash, point P dash will be maximum intensity. Between this O dash and EA, the number of half period zones are odd, then we will be getting the maximum intensity at point P dash, else we will be getting that means if the number of half period zone is even, then the point will be minimum intensity. So depends on the number of half period zone between A and O dash, we will be getting the whether it is, we will be having whether it is maximum intensity or minimum intensity. Now if I am taking another point, that is P double dash, that is in the geometric shadow region. Again I am drawing a line between S and P dash, that is meeting at point O double dash. Therefore O double dash is the pole of the wavefront with respect to the P double dash or P double prime. If the wavefront is divided into half period elements, obviously the upper part of the wavefront will be upper portion between X and O double dash cut off by the obstacle, and only the portion between A and B. Now you see between A and B, this completely exposing at point P double dash. If the number of half period elements exposed by the region AB is odd, then the P double prime will be, the point P double prime will be maximum intensity, and if it is even, it will be minimum intensity. But as most effective central half period strips between O double prime and A are cut off, then obviously the intensity falls off rapidly in the region of the geometric shadow, and the maximum and minima cannot be distinguished separately. The intensity distribution due to a wide aperture is shown like this. Therefore, wide aperture is shown like this. Here it is uniform illumination. Then it is near to the slit edge, we will be getting maxima or minima, depends on the number of slit between these 2 points. If it is narrow, what happens? Supposed to be at the point P, we will get the number of half, with respect to point P, supposed to be the number of half period zones exposed at point P between A and B, if it is the number is odd, then the intensity at point P will be maximum, and if it is even, the intensity at point will be minimum. That means the point P can be either minimum or maximum, depends upon the number of half period zones between A and B, right. If we consider another point P dash in the illuminated region, then the intensity at P dash will depends on the number of half period strips that can be constructed between A and O dash, and obviously if the number is between A and O dash is odd, then P dash will be a point of maximum intensity, and if it is even, then obviously we will be getting the minimum intensity or dark. If we are considering another the point in the dark region P double dash in case of narrow slit, then the region the geometrical shadow, the O double dash is the pole over here. O double dash is the pole on the wavefront with respect to with reference to the point P double dash or P double prime, and the intensity at point P double prime will depends on the number of half period zone that exposed by the slit AB in the upper part of the wavefront above O double prime, that will be cut off completely, and if point P double prime is far away from E, if it is far away, then the maxima and minima become indistinguishable, and there is no any marked transition between the diffraction band observed in the geometric shadow or in the illuminated region. In the intensity distribution on the screen can be shown here. So, you will have the point P either maxima or minima depends upon the number of zones, and then this will be varying like this, and away from the point E, then you will be getting and an indistinguishable maxima and minima, and therefore that will be completely a dark region with decreasing intensity, you can see. So, with this I am summarizing the session here. So, we have discussed how the diffraction pattern formed at a straight edge, then we have derived the condition for the maxima intensity and derived the condition for the minima intensity. Then we have discussed how we could explain the formation of diffraction pattern due to narrow slit and using Huygens Fresnel assumptions. I hope you understood the concept well. We will meet again in the next session. Thank you.